Hello, welcome to our webinar about Part Analyzer. My name is Matt Campbell, CEO of Medema Labs. We're a new software company focused on mechanical design and manufacturing software solutions. And our first product, Part Analyzer, provides feedback on how to best manufacture your metal parts. Let's start with understanding the use case for Part Analyzer. We're focusing on design engineers. Design engineers typically make or change designs in their favorite CAD software like SolidWorks or NXCAD. And before going to CAM, they'll send their digital files to Medema Part Analyzer. And our tool will provide informed manufacturing cost, timing, and plans that the design engineer can use to improve the design in the next iteration. Typically, this is done with people that are distributed throughout a company or through multiple companies, but we're hoping to tighten this feedback loop by having Part Analyzer provide that useful predictions of the manufacturing details early on. Part Analyzer is part of a family of products called PCM, or Product Cost Management Solutions, and there are a few other current product cost management tools in existence. They focus more on system level issues. Part Analyzer gets really into the manufacturing details. For example, inside of our tool, we have artificial intelligence considering multiple part orientations during milling. We look at dividing a part into smaller parts to reduce manufacturing time and cost. We essentially are performing optimizations over countless permutations to try to find the best solution for your part. And so, as I mentioned on the previous slide, we're really focused more on the design and manufacturing engineers, whereas other PCM solutions are looking more to help your industrial engineer optimize supply chain logistics. We get really into the computational geometry of the part and run some detailed simulations to find these optimal solutions. We're not doing simple lookup tables. So we start with a simple 3D representation of the part, and we'll show you this in more detail in our demo. First thing we do is we optimize the stock geometry. So based upon a lot of stock sizes, we can find what's the best part to start with. And here we have just a green cube around the original part. Then we reason about all the detailed CNC operations, peripheral milling, roughing, finishing, multiple rotations that would have to happen. And we're left with a part in this bottom corner. You actually see there's some red bits that were very difficult to machine. And so we show those to the users to provide this feedback. As you'll see from the demo, the feedback is both in pie chart form as well as animations showing the creation of the part. We have a beta test available and would love to have you try it. Here's a web page showing that it is available in the Microsoft Store for easy download and installation. Simply complete our software license agreement, SLA, on our website. The website is simply medemalabs.com. And we will send you the promotion code that you can put in here at the Redeem a Code button. If you test our software, you will receive up to 50% off the annual subscription for the software for your company. We're just getting started. We have a lot of plans in the future. We're looking at assembly planning. This is an area we've been working at for the last 10 years. So instead of a single part, reasoning over many parts. We're working on lathe operations. As we'll show you in a bit, we are doing some additive, but in the future we're going to be doing more comparisons between additive and subtractive. We're bringing in machine learning to calibrate our models. And we learned about we recently received some Department of Defense funding to improve the request for quote process for contract manufacturers. So not only are we focused on designers, but also machine shops that are responding to orders coming in. If you need a custom solution, we're here to help. In fact, we've helped a number of clients make simulations, for example, for friction welding or for doing cost to mass trade-off here on a topology optimized part. So we have expertise in this geometric-based cost modeling, and we're looking to make specific solutions for specific clients, as well as a general product available to everyone. Contact us at contact@Medema Labs, and we'd love to talk to you about how we can help with your manufacturing. Okay, off to the demo.
Hello, I'm Brandon Missoni, the Chief Technology Officer at Medema Labs, and today I'll be showing you the demo. Once you have downloaded Medema Part Analyzer, it'll just start up like any other application. So what we're seeing here is an empty session, and what this is asking for is just to load in some 3D parts. So the idea here is you export your parts from CAD as an STL file or some other tessellated file format. And here I'll go ahead and select a part. And now it's loaded up, and we just need to select the material and units. And if those are predefined in the file format, it'll pick those up as well. So first I'll go ahead and we'll look at titanium, and this unit is in millimeters. And I'm picking titanium specifically because we can run additive manufacturing on that, as opposed to aluminum, where the material is not as widely available. So I'm going to go ahead and run now some of these simulations over on the right side. These are really the optimizations that are considering all those different options that Matt talked about. So in standard stock, in closed die forging, and in this hybrid substrate optimization, it's going to be considering that automated manufacturing plan. And then when the solutions get done, they'll show up on the left here under manufacturing plans. So here's that first one, standard stock simulation. And what we see here is a representation of the stock material in transparency over the original part. And then I'm going to go ahead and show the plan analysis first, and then we'll come back to the cost analysis. But if we look at the plan analysis, we can just watch the processes that are required to manufacture this part. So the first is fixturing the part, then it's doing peripheral milling, roughing, and finishing. That's doing some drilling operations, flipping the part over, and coming from the back side to finish it up. Now, unlike the example Matt had in the slides, this one doesn't have any material that wasn't removed, and that's because I changed some of the settings. And there are quite a few settings you could change depending on what kind of tools you have available and tools and machines you have available. For each of these individual processes, we can then, so these are all determined automatically, and for each of these, so we'll go back to peripheral milling here, the geometry that is removed is defining the parameters for the feeds and speeds. So in this case, there is a depth, and depending on the tool length, that'll determine a number of passes, and that, along with the feeds and speeds, we can calculate things like material removal rate. And so some of these inputs are from the tool manufacturer, and these are all in a spreadsheet that could be customizable to each individual customer, or we could pull them from suppliers like Kennametal. And then for each of these different processes, you'll see these numbers change accordingly. So in that case, peripheral milling was the highest material removal rate, and then roughing, and then finishing gets slower. As well, we can look over in the cost analysis tab, and in this tab we can see those, let me close this up, we can see the acquire process here, which is the material cost, and in this case that's forged rectangular bar, it's $2,240, and we can see the geometry of this stock shape. And then if we open up this milling operation, we can see the individual parameters of this and click on these individual pieces that we saw on the other slide. And so it's important to note that the determination of what material to remove and which operations to use is all determined automatically within the tool. So I didn't have to do any selection as a user to identify that. It's all really based on the inputs and then also on optimization. So now I want to get to some of the results of these other simulations, and I'll go over some of these a little bit quicker. But here, so we've got the closed die forging simulation, and this again has the acquire process and a milling operation. And if we look at the plan analysis, we'll see a different plan where it also removes all the material, but from a different direction because of how the forging was defined. And so now you can start comparing things like standard stock, like a forged rectangular bar, compared to a closed die forging. And in this case, since it was from titanium, there's a lot of wasted material in this stock. And this is a lot of material. So $2,000 is a lot more than you'll see for most material costs. But we are talking about titanium here. And I ran that specifically so I can show you these hybrid simulations. So with the hybrid, this is additive and subtractive. And the idea here is that the optimization is determining where the best substrate plate is in this case. And in that case, it puts it here. And you can see that it's kind of a non-intuitive height. And that's really where it found to be optimal. And then on top of that, we have this 5-axis wire feed directed energy deposition, which is just metals additive. And as we see that, we'll have a final machining operation. And this can actually be considerably cheaper than even our closed die forging solution, depending on how much the material costs and the different settings. So those are a few of the different simulations. We have one more here called part divider, and this is maybe a little more complicated of an optimization just to show you kind of what we're capable of. And in this case, what it's trying to do is find the best smaller stock sizes to put together such that the material cost and machining cost is minimized. So here it decides to do 3 water jet plates that are going to be joined together. And depending on what your settings for joining are, just the joining cost, we just have a basic join. So for each of these, they're $20. But if you increased that, you would then have less joins. And if you lowered it, you could have more joins, just depending on kind of what you're looking for and what kind of joining operation you're trying to mimic. So here we'll click on another one. So here's another example where it splits it into a little bit more pieces. So that's the overview of Part Analyzer as it currently sits. We're looking at developing additional pieces for the automated CNC operations, as well as expanding this list of simulations for individual companies that are interested in it. And kind of what I'm not showing in addition is there's a bunch of settings in the background that'll need to be tuned for individual companies to get this to be really accurate for each of those companies. So I want to thank you for listening today. And if you have any questions, go ahead and send those to us at contact@medemalabs.com. Thank you.